Cool. All right. So I realized like I've been talking about LLMs and using them to create DSLs, domain specific languages, for quite a while. And then recently I realized that maybe not everybody knows, or like probably a lot of people don't know the theoretical backing behind it. I tend to forget how much I gathered over the years. And then this paper was shared recently, I think by Major Tom of Facebook, not transforming code with an LLM, but using the LLM to write code to do code transformations, which I actually have been doing quite a bit already. And so I thought, not only is this really effective, but at the same time, Zach, talked about using, wouldn't it be great if you could use an LLM to automatically do vectorization optimization on his PyTorch? It's perfect. That's really cool. And I actually spent some time to make it work. And while doing that, I realized, okay, let me give the theoretical backing, because this is kind of like the OP tool to use LLM for, right? Like this is really super, and it actually goes to the core of what JSON are. The first section here is going to be abstract syntax trees, which is a data structure for a lot of the things in computer science. So an abstract syntax tree, it's like a hierarchical tree data structure, right? So you have nodes, and then you have child nodes, and that's about it. It means you usually don't have back pointing arrows, which would more turn it into a graph, right? Like this is something. And the main purpose of trees in the domain that interests us is to use them to represent syntax, right? So it can be programming languages, can be markup languages, it can be data serialization formats. Really, most of the things that, let me record this actually. Oh no, can someone record? Yeah, just recording, cool. So most of the things we deal with, and especially most of the things we use LLMs to generate or transform, are representable by an abstract syntax tree, right? Like every programming language actually gets parsed into an abstract syntax tree, but JSON is also a tree, right? Like if I have this JSON, I can actually represent it as a tree, which has an object. And then for each key, I can have like a child node. And then for each key, I can have a child node that's the value of it. And then as such recursively, right? So this is the first thing where I realize often people misunderstand me when I say like, oh, JSON is just exactly the same thing as XML or so, is that or YAML is, if you have this YAML, it's actually exactly the same tree, right? So in a way, JSON is the same as YAML, except that this one's more readable, has like different pitfalls. And HTML, for example, is also easily representable. Not only is it XML, but also, right, it's like the DOM that you see in your browser when you go to the DevTools is the representation of this tree that you get from parsing the HTML. And then when you use JavaScript, you're going to modify this tree. You're going to add like child nodes. You're going to remove them. You're going to move them around. So it's all AST manipulations. So far, so good. Trees everywhere. And where it gets interesting is that you can represent code as trees, right? Like if I have this Python code here, we know it's a function definition of a function called greet that takes an argument names, that has like a body with a return statement of a format strings that has, right, like all of this stuff. If you can, for example, represent it as a tree, as a function definition, as a root, and then the first child of this root is going to be the function name. And then the second is going to be, in this case, it like encoded the keys. And as you can see, there's many different ways we could represent this as a tree. Like, why do we have a return node? Why do we have a join string? Why do we have a constant? Those are decisions made by the people writing the parser. So we'll get to what parsers are in a bit. And there's different kinds of trees. This is where my slides get a little bit messy. Can I make this full screen? There we go. For example, you could have a parse tree that is really, really explicit, that encodes all of the things, every little detail from the programming language grammar that is necessary for a compiler, for example, to compile this code. But this is pretty harmless because it's Python. Look at a C++ parse tree in Clang, and you'll see what I mean. It's like literally thousands of nodes of crazy stuff. Often, as humans, we want like a much simpler tree, right? Like this is much easier to work with than if we have this. And not only if we're not compiler builders, simpler trees often make sense as well. Yeah. There's a whole process that I'm not going to go too much into because I didn't want to turn this into a whole compiler construction lecture. But the way we transform something like this into a parse tree is usually first a tokenizer that just like similar to what tokens are in an LLM, it like recognizes specific words, right? Like also like, oh, if it's like numbers in one word, then it's going to be a number. And if it's like ABC with a lowercase, then it's going to be an identifier. And then if it has like a quote symbol, then it's going to be a quote symbol. So that would be the first step, is like having a tokenizer that transforms strings into like little words. And then there's a parser that takes these little words and actually creates the tree out of them. And if there's like invalid grammar, it will tell you like, oh, well, you can't like put two numbers next to each other, for example, or you can't, like, you have to close the string. So that's a whole field for itself. It's kind of a solved problem-ish parsing syntax. And there's some pretty great tools to say deal with programming languages and get information out of them. Like TreeSitter is a nice AST parser for a ton of programming languages that's geared towards human readable syntax trees and also catching syntax errors pretty easily. So, yeah, compilers is just great. Like I really enjoy it. And I think LLMs are really cool to learn that stuff, but I can get into that in a different lecture. Hopefully you get some ideas from this one. So how do we work with ASTs? Like this is all nice, but like this is not code, right? So there's one way we can do is like just implement our own, right? Really is just a node has a value in children is like one way of doing it. You can make it a little bit richer by giving every node like attributes and things like this. But this would be a good start. And then to represent the tree we were looking at of this thing of like A is equal to the addition of B plus the multiplication of C and D, you would write it like this, for example. That would be one cheap way of doing ASTs by hand. And there's other ways of doing it. Like a lot of programming languages come with their own AST parser library. But you'll basically end up with some kind of similar data structure. But the question is like, now we have it as a data structure, like that's cool, but what do we do with it? This is where a couple of design patterns come in. Like the most powerful design pattern I know in programming is called the tree walker. They're sometimes also called like tree search algorithms, but this is basically you usually define a function that works on a node, and then you give that to a walker that's going to walk through every node in the tree and call your function on it. There's different ways of doing that. You can do like depth first, you can do breadth first, you can do like on enter, on exit, like there's different types of walkers. I recommend you like learn a little bit more about them. It's once you get the concept, it's a fairly easy thing to remember. And in practice, it's like just writing a function that's called visit node. So for example, if we were to actually evaluate this, right? Like how do we compute this thing? We have a tree and now we can use a walker. So this code is a little bit long. So we create the tree as we had it before. We have our visiting function evaluate. You can look this up in the handout, by the way, like I'm not going to go too deep into it. And so this is going to check, oh, is it an assignment node? Then I'm going to assign the value of recursively evaluating the children of this node. So AST walkers often look like this, where you like, what does this mean? Like when the node is equal, I just assign. And then when the node is plus, I just like do plus. And then when the node is times, I just like call times. You're like, this is ridiculous. Like where's the complexity in that, right? Like, but it's also like a little bit meta. It's like, is this plus related to this plus? You can get really deep into the weeds here. It's like a little bit mental, but also once you understand how it like recursively walks the tree by calling itself, for example, then it suddenly becomes pretty easy. So the way you call it, right? Like if you do this, it really is just going to compute 14, right? Like it's going to go to the assignment, then it's going to say like, well, we don't have the value of the assignment yet. Let's go to evaluate. And it's going to say like, oh, it's a plus, but we don't know what we're adding. So we're going to evaluate the left node and we're going to evaluate the right node. Then we're going to add them. On the right node, it's going to be like, oh, this is a multiplication. Let me compute the multiplication. And then at the end, it's going to say like, oh, this node is a variable. Let me look up the variable value. Or it's going to be like, oh, otherwise it's a float, just add the number. So this is what pretty much all interpreters and compilers actually look like, right? Like they do transform or evaluate a tree. You can do that with the AST module in Python. So how much time do we have? Yeah, we have time to maybe run this. Let me open cursor. Let me open cursor on my Vault. Obsidian Vault. Then let me go to the handout. We are in the live AST. So this is the slides that I'm showing right now. We're just going to go to this code example here. This is the example we just looked at with the recursive calls to evaluate with our like manually written walker. And then if I call it, if this works, it used to run yesterday. Why is this not working today? That's the typical like, oh no, it runs here, right? Like it will output the thing here. And so what we can use LLMs for, which is really nice, is like I can say like add verbose logging to each evaluate call. This is why learning compiler construction with LLMs is pretty nice, except it doesn't work here. I don't know why, because it's a markdown document. It probably struggles quite a bit with it, but you can, because this is pretty dry stuff, right? Like you look at the code and it's like kind of hard to understand what it does, especially if you have ASTs that are way more complex. However, with LLMs, you can build a lot of tools to actually inspect your trees and do all of that stuff, right? So it's a really nice kind of setting to do that. And then if we use the, let me see if I can make, is this big enough? Is this small enough? I'm going to zoom in a little bit. So here we use the Python AST module, and Python is able to just parse Python code, right? And here what this does, I think it like just inserts a print statement at the beginning of every function. So here the visiting function is already kind of dispatched by the node transformers. There's like a whole API to do node visitors, node transformers. I'll quickly touch upon it, but this is something you can look up on your own. And then if I call it, you'll see it actually modified this code and added a print statement. So this is a code transformation, right? This is actually a code transformer that adds a print statement to every Python function. And the funny thing is that LLMs kind of do pretty well with it. And this is what this paper is kind of about. I actually haven't read it, so maybe I'm wrong. But if you do something like this, create a Python AST node transformer that logs the return value of every return statement in functions that start with slow no, right? Like this, it's kind of a pain in the ass to write by hand, even if you know node transformers pretty well. But right, it like visits functions, says like, oh, does the node name start with slow no? Okay, then visit the node recursively, right? Because it could have like nested function definitions. And then it looks at the body. And then if the body is an instance for every statement in the body of this function, if it's a return, then insert like a call to print and then extend the body with this. So I'm not fully sure if this is going to work. This is always like a little bit, I'll get back to it. Like AST parsing code is code that is very prone to hallucination because it's very like meta. It like talks about functions while defining functions. It's like very easy for LLMs to get confused. It also, depending on the API version, which changes in subtle manners, it will like, use the wrong API. So this is code that usually you kind of have to touch up by hand, but also, right, like it worked, right? This print call thing is like not super elegant, so you could potentially make it a little bit prettier. But overall, it at least like puts stuff into a shape that's like pretty nice. And going back to the slides, I'll touch upon this a little bit more, right? So we have our modifying ASTs. We can generate code out of an AST, which unparse. And we have a node visitor, a node transformer API. We can generate visitors and transformers using LLMs. That's what I just showed, right? You can do things. So this is what I was touching upon. AST matching and generating code is often prone to hallucinations, like a very brittle kind of API to deal with, because it just uses a lot of programming jargon that has to be getting right. So one way to tackle this is to generate a tutorial with many self-contained examples. So you take an AST version, you generate a lot of examples saying like, if you want to insert a print statement, this is how you do it. And then if you want to match functions that start with X, and this is the pattern to do it, that helps a lot. You can generate a reference document for exactly the API that you're using. So maybe it's called function def in Python, but it's called function definition with tree-sitter Python, like those kind of things. It's always good to put them in the context window when you're generating LLM code. You can take the tutorial, run and fix the examples, and then use that in the context window, right? So I did spend a little bit of effort actually doing that for this talk, just to see how hard it would be. So here I have a whole tutorial about using Python AST to do validation and transformation, right? So I ran all of these, fixed all the APIs that didn't work. And now that I have this thing, if I put it into the context, right? And then I repeat what I just did previously, where was my prompt here? This prompt here, if I repeat this, but however, I add my AST documentation. AST documentation, does it do it? Gosh, it's hard to reference things that have Python AST. There we go. So if I add this to the context window, it will probably do a little bit better job. It didn't use Astor, which is an outdated API library, and then it does this kind of stuff. So that's ways to deal with it. It will still not be great. It often makes sense to then touch up things by hand. There's a couple more patterns that you can use, which I put into the handout, which is like code templates, and just have it fill code templates instead of generating the AST. So yeah, this is real world use cases, right? You can use them to do linting rules. So linting is both matching patterns and saying like, this is a bad pattern. It's also providing fixing instructions. So I generated a tutorial on how to generate lint rules with PyLint, right? And if I do this PyLint tutorial, and then I can say like, make a linting rule that warns if a class beginning with AI in action is missing a method, YOLO, right? Like these kinds of things, which are easy to say in human language, but then like, how do you write code to do this? It's like freaking tedious. If that method is missing, suggest a fix to insert it, right? And this is kind of like, as said, it's like a little bit prone to hallucinations. But once you get comfortable with the AST method, you usually are pretty fast in like fixing these things. And this is like highly added value to your code base, right? So I used to deal with freelancers messing with my CSS, and they would like add like some weird ass classes and stuff. And I was like, dude, like don't add a rule to set the font size if it's not applied to a container. Like those kinds of rules were really, really useful because the freelancer wasn't able to submit code that didn't pass those cases, right? But this is a really good value. Then optimizing code, right? Like I'll get into this PyTorch example. So This is a simple torch node transformer that recognizes for loops and replaces them with torch operators, right? So if there is a for loop with this pattern inside, so where you're manually doing a vector addition, for example, which is kind of a lot of code to write to do the matching, right? Then it will replace this with an assignment to torch add. I wonder if I can just run this Python file. Yeah, so there we go. The original code is here, right? With some manual loops. The pattern matcher was able to match those and replaces them with torch add. So there's a bunch of tools that do that, right? But it's like really nice to do like custom matching stuff where if you define your own API to do these things, they can say like, well, can you replace all these like old manual codes we used to do before the API refactor and just replace them with this new stuff? And instead of doing it with an LLM, which is expensive, slow, and like often, doesn't fully get it, in one inference, you can get the transformer and then you just let the transformer run. And this is exactly what this paper is about. And now you know how to do it. The large scale refactors, optimizing code, generating tests, generating documentation, generating codes. That's all kind of the same stuff you can do, right? Like generating code generators is a pretty nice thing to do because at that point, you can generate code without having the LLM in there, but you benefited from the LLM to do the tedious part, which is you just input natural language of what you wanted to do, but now you get like a reproducible rule. And if the rule's like, not fully correct, you can quickly correct it. So you can also do this transformation on ASTs, on any kind of AST. So that means that you don't need to only do it on programming languages, right? You can do it on your JSON, you can do it on your YAML, you can do it on your XML, you can do it on your CSV, you can do it on any data structure that you have as well. Use it to say, have some data declaration in JSON and then generate, say, a REST API for it, right? So these are things that you can actually try out very, very easily, which brings me back to learning these things that Cable was saying, right? It's like generate a small JSON data structure, so something like this, then generate an AST walker that takes an instance of this data structure and generates Python code to do a REST request. This kind of doesn't mean too much, but the model is just going to be like, yo, sure. But here you'll see an example of this, right? You'll have your JSON, it's going to generate this, and here it's going to use a template to do it. So this is one way to do it, right? But you can also do it, use the AST module. It likes to use outdated packages. So that's a little bit annoying. It's stuff you can put into your cursor rules. Right. And now it's going to generate AST things. And then out of the AST, it's going to then create the Python code after that. So it's nice because you don't have like strings everywhere that don't like, syntax highlight and stuff like that. Also, it's a little bit less readable by a human potentially. So both approaches I like doing. Like sometimes I just want to have like string templates. Sometimes I just want to have like AST stuff. So let me see if I'm going to let it finish generating. And then, oh my God. See, it also just like uses a lot more code. But I actually want to run this. All right, cool. Run it, and then we'll let it yap in the background. Going back to our slides, this was the first set of my lecture. Are there any questions so far? I'm annoyed that like sometimes it doesn't really get that I want to have a code interpreter. I need to be more careful. So how do you modify cursor rules to not use outdated libs is like edit your cursor rule and say, don't use outdated libs. Yeah, I kind of a joke, but I say like, oh, this is, don't use Aster, for example, this thing. Because it does know, yeah, it's so see here, Aster is not in here. So what I would do is don't use Aster, use AST on parse. Like this is literally what I would put into my cursor rule. Because it does know
Cursor rules.
so I don't have that in my cursor rules, but this is what I would do. I don't think I have a cursor rules in here. I can show maybe from another project, corporate headquarters. Here, my cursor rules kind of looks like this. Use Cobra for CLI application. Use context always when async is involved. It tells how the packages are named. Like it says, use OS read file instead of the deprecated IO util methods. So that's usually enough. And it's a weird thing with LLMs. It's like kind of when you ask the question, you can just like kind of write the question as a statement and it kind of works. But that's how I would do it, right? It's like here I said, please don't use Aster. And then, man, this is way just like too much context in here. And ChatGPT has been bugging out on me all day anyway. Freaking annoying. Let me try this again. Yeah, it's doing this weird thing in like Firefox where it's also like, I don't know. Demo woes. Because it works if I use Chrome. It's just, I don't know. They're not like, they should use Sonnet more, I guess, when programming ChatGPT. And then Chrome hangs. I'm going to leave it there. I'll come back when it works. So I'm going to get to the second part of my talk, which is, okay, what's all this AST stuff useful for? You already saw quite a few use cases of them, which are really, really cool, right? Like code transformation, code optimization, refactors, validation, blah, 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 blah. But where it gets really, really interesting is when you create your own languages, right? Like we saw how you can use JSON and YAML, for example, as an AST representation already. So you can really easily create programming languages without having to write a whole parser and tokenizer. You can just use JSON or YAML as like straight AST representation. And in fact, Common Lisp or like Lisp in general, you know, all these like parens and stuff, they are actually just a tree. Like when you write Lisp, you actually kind of write the AST straight out, which makes it a little bit weird, right? Like you don't have that syntax sugar of like having semicolons and colons and, you know, all that stuff. But also it makes it very easy in Lisp to transform Lisp language as an AST. That's why like Lisp macros are this kind of like revered thing, is that really is just like a very easy way of creating what I'm going to introduce, which are DSLs. So let me just try the thing that we just had, which is create a JSON data structure, then use AST and AST unparse, not Aster, to convert these data structures into Python code that represents a REST API, and then run it and print out the generated code. So I hope that this will kick in the code interpreter. Yeah. And so I'm going to let it running in the background. So what are domain specific languages? They're programming languages that are really, really tailored to a particular problem domain, right? And yeah, this is data is code, code is data. That's basically what ASTs are. They're the data structure to your code. And so when you write a programming language for a particular domain, you can really like tailor it to what it's doing. So for example, well-known DSLs are like SQL is a DSL to do database queries. HTML is a DSL to represent markdown documents. CSS is a DSL to represent like rules to style a document, but you can make it anything you want, right? Like maybe I want to have a DSL that's used to specify like data transformations, right? Maybe it could look like this. Load the file user CSV, apply the filter on the column H with the condition greater than, then sort the column, and then export it as adult users. Pretty clear what it is. There's no weird programming stuff, right? Like even though an LLM could probably generate the code for this pretty well, it still has a danger of using the wrong APIs, using the wrong, making little subtle things. And yeah, certain languages are used to create DSLs quite a bit. So say like Ruby, Lisp that I already mentioned, but also flexible languages like Lua and JavaScript. They're so flexible that it's easy to implement different styles of programming, right? Like in a way, an API is kind of its own DSL. There's value in using Ruby. I'll get back to this, what internal versus external DSLs are. So first I'm going to stick with these like YAML things. So as we saw, a YAML document is an AST. So you can kind of like transform this into a data structure like this, right? So you have a program has a sequence of steps. The first step is load file, takes an argument file name, and then you have filter, and then you have sort, and then you have export. Really, really cool. You can validate it, right? You can say like, well, you can have 2 load files in the sequence, or you can have a filter after an export. So those would be easy to just flag.
The question in the chat from Yano SC around why to use YAML or Python instead of generating a tree sitter.
So, tree sitter per language and per tree sitter version, you have different AST versions. I like to use YAML because it's just like programming language independent, right? It's like I create my DSL that if you use Ruby or if you use JavaScript or if you use Go, you can actually load the same YAML file and then work with this DSL. I'll come back to this, like which target format should you use? I like using YAML instead of JSON just because it's more readable and less tokens, and it's easier to stream, right? Like if the LLM generates just this, I can parse it. If it generates just this, I can already parse it. If I generate just this, I can parse it. So it's like, I don't know. I like using it. And so this is kind of how you use these DSLs in practice, right? You convert the code into an AST. You can validate the AST and say like, look, the thing that you gave me is incorrect. Then you can use the patterns that we looked at, the visitor and the transformer, to either interpret the AST or to transform it into something else, say code generation, right? And yeah, whatever, optimization. So for example, you can use YAML to create like a DSL for your unit tests, right? So if you want to like unit test validation of your validation code or whatever, instead of having it generate like a lot of code that does these unit tests, you can just generate like a big YAML, interpret it, and then run the unit tests on it, right? Like the advantage is like way less tokens. You can easily validate that the LLM generated useful stuff. It's often more readable for humans, right? Like I think even if you're not a programmer, you kind of understand what this is. I can visualize them, right? Like I can again using LLMs, I can do things like this. So, oh, look at that. So I don't even know which JSON data structure, or it created like a REST API description, whatever. And then it converted it to, well, no, this is wrong. You get the idea. Sometimes it really doesn't understand things all that well. That's why what we just saw, by the way, is an example of why I like using completely off-kilter examples, right? It's like create a YAML DSL to milk cows, then write a Python AST-based DSL compiler that transforms the DSL to Python code, use AST unparse to print it, create an example, and run it. So we're going to let that run in the background, and then we'll go back to this, create a HTML viewer for this. Actually, I'm going to do this in Claude because it has nice JavaScript generation. So I'm pasting my user test cases, right? And like, so I can load it in my unit test runner, but I can also like display it and like maybe make even like an HTML interface to create new test cases, or, you know, maybe my users can create all of these things, or maybe I automatically create test cases out of like a log file, something like that. So this is why I really like the YAML stuff, right? It's like make a text area to paste some YAML into, then also generate 3 more examples of YAML. So it's really, really easy to get LLMs to write really useful code around this DSL. If you want to do live demos, I'll use OpenAI. So we're getting to internal versus external DSLs. So external DSLs are independent of the programming language they're going to be interpreted in. A very cheap one is using YAML and JSON, all of that stuff. If you want to do a more custom language, like say regular expression or SQL, you're going to have this whole like parsing and tokenizing and all of that. Certain frameworks like Racket is a really interesting language because Racket is based around the concept of building DSLs and kind of has a lot of inbuilt functionality to create not just like Lispy stuff, but actually allow you to implement all kinds of programming languages. There's like a ton of stuff here. So if you do want to look into like learning DSLs and compiler construction, I kind of really highly recommend Racket. And it being used a lot in academia, there's a lot of courses around it, especially actually from Providence, where I live, from Brown University. One of the Krishnamurti, Providence, Brown has a lot of courses using Racket to teach compiler construction. So you can go look at his stuff, for example. Actually, I should have put that into the references. So see, goddamn, it didn't use the code interpreter. It's like, it's so freaking annoying. Claude, very nice. Let's copy it in here, parse YAML, visualize it, right? Like this is just really, really nice. So for example, you can use YAML DSLs to say represent UIs and then have like a streaming preview of this. Another pattern you can use is, oh my God, I'm almost at the hour. Let me see how much I have here. Gonna go really fast. Just, you can look up the details in the handout and all the code in the handout can run. I've ran it, I've fixed it. Internal DSLs actually are embedded within the host language. So they are actually part of the programming language itself. And the cool thing about internal DSLs is that the LLM is going to be able to inject real code into it, which makes them much more flexible, right? Like if I go back to this example and I want to have like a custom validation function, can't really represent that in YAML. I would have to either create special nodes to do my new logic. If this was an internal DSL, which I can show, because this is why LLMs are really cool. If I go to Claude AI, it's like, make a Ruby DSL inspired by this, and then add a few dynamic Ruby validation examples, right? And you can kind of, what the? See, this is a Ruby DSL here. It kind of is a nice syntax to represent test suites, right? It's sort of like, oh, test suite, and then the name, and then do, and then there's a case, and then do, and then there's an input, and then, but you can actually pass in like real Ruby code at the moments where it makes sense, right? Here, it like has custom print code. That's not possible with the DSL. So with the external DSL. So it gives you this flexibility. The downside is that suddenly you're running code that's created by the LLM instead of creating something that you can sandbox very easily. So, right, like I wouldn't put this in the loop on a user-facing application, but I would very much put this into a user-facing application because I can validate what it does, can make sure that this is not going to delete all my files or like read the database or so, right? So this was internal versus external. So for example, if we have a YAML DSL to represent a UI, this is kind of a mix. It like depends on the fact that there's going to be a handler. If you do it in Python, for example, this is what an internal DSL in Python could look like. And the cool thing, again, and I guess I shouldn't copy paste like this. I should copy paste like this. You can go to Claude and it's like generate alternative DSL proposal for this in Python, right? And so you can use the DSL to actually look at different takes on how a DSL can be created. And in fact, when I'm bored, I go in here and then I will do things like create a YAML DSL for wet scraping. And then I'll just press regenerate just to see what comes out because it's being trained on so much formal language, it actually generates pretty good, consistent, DSLs. And so, all right, well, maybe that's interesting, right? But maybe I would say like, oh, add some proxy and load balancing instructions. And so you can kind of iterate on things. And I highly recommend you play around with this, right? It's you don't need to run the code. Just look at like the different patterns that come up. Like you can see, oh, what is this syntax, right? Like, why did it choose this? Because this always refers to something in its training corpus. Like there's a reason why it knows about proxy lists. Like maybe there's, it's and then you can regenerate this first one, for example, right? It's every time it's going to do something a little bit different. Right. So maybe you can modify this and say like Lisp inspired by JavaScript. So you can really just like sit on the couch and just like actually inhale, put some like patterns in your brain that might come up useful in the future. And that aside, data validation, you can use it for configuration. It doesn't need to be code, right? And then this is the pattern, right? Create a YAML DSL for XYZ, you regenerate and iterate. Then you say like, oh, write a spec for the DSL. So pretty good prompt. And then you get a really clear spec out of it, which can reuse in the future as context for generating this DSL, right? So we're going to take this. We're going to do a completely new chat. I'm going to paste this as a context, and then say like, create 3 windows about dog therapy. Because now the next value of LLMs is that you can generate a lot of examples for implementing your DSL, but also for like actually the problem you want to solve. And imagine you have a preview function. You can actually give this to a non-programmer user and they could type in like, oh, make a UI for dog therapy. And then they can iterate until it looks good and tell you like, look, this is the YAML that I think looks good. Can you implement this for me? So here you end up having, 3 different windows about different dog therapy stuff. And this is actually, I find really hard for me to do because like once I've written the second example, I'm just like tired and I won't have good ideas. Yeah. So actually this is the cycle, right? It's like once you have the examples, you can write a program that just executes the examples to make sure that it works and then feedback the errors into it. I still do it manually, but I think that would really benefit from an agent at this point, right? It's like you iterate until the spec is like how you want it, and then you iterate to implement it. I must say that this kind of suffers from the same AST throwing stuff. It's like sometimes if you don't get it to write the interpreter right straight away, stop, take a walk, probably write it from by hand. It's very easy. At least that's what I ran into, to like really rabbit hole yourself into implementing the DSL when really it's about taking a step back. Because if you remember, right, like this code we looked at to do the evaluation is like the code looks like case star, then do star, and then case minus, then do minus. It's like it's very confusing to an LLM just because it repeats so much, but in like subtly different contexts. But targeting a DSL often leads to less hallucinations. There's less ways of getting this wrong, right? Versus having a lot of like UI library dependent code and stuff. And the really cool thing is like way less tokens. So it's really fast, right? Like here we generate like 3 UIs and I don't know how much this is, like 400 tokens or something. Paper to sandbox, streaming, we already had all of that. Transform, hue and stuff. I'm going fast because you can look it up in the handout. And let me see if there's something interesting in here. I've got a list of patterns that you can use to implement these in addition to the visitor. And then one thing you can think of is intermediate DSLs, right? So if I have some kind of DSL to represent database queries, it would kind of look like this, right? And this is great, but also it still is like a lot of jargon for what I want to do, which is like, oh, give me all the 30-plus-year-old employees that are in by department or whatever. It still is a lot of jargon that it can get wrong, right? Like this is fairly complex, but it's a good DSL to implement SQL generation. So what you can do is you can create, right? Like this is what the compiler looks like. But what you can do is like you create on top of this intermediate DSL, you create your own DSL for employee queries, right? So now if I say like, oh, query all the employees above 30 years, this is much easier for an LLM to generate without errors than like this stuff, right? Like here it has to get the join correct. It has to like do this like where thing. There's a lot that can go wrong. However, if I do this, nice. And now I don't need to write a SQL generator for this DSL. Instead, I just need to transform this tree, right? Like AST transformations into this tree, which is actually fairly easy to do, right? Because they will just say like, well, employee query, that's a select from employees with departments. And then age above, that's just like a where query of the age above. So these transformations you can do with templates, for example, right? So this is converting this new DSL to the SQL DSL. And now you can completely validate that without having to validate SQL strings. You can just use your previous DSL validator and be like, yeah, is this new thing correct? Building up step by step is what a lot of compilers do, right? Like when you say compile C++, it will like first parse it into an AST for C++, then it will transform it into something that's called an SSA graph. Then it will transform that to an intermediate representation, which is called MIR intermediate representation. Then it will like transform the IR into simpler and simpler versions of itself, applying optimizations until at the end it takes the IR and generates machine code. So here I've got a bunch of examples.
We're in our last 5 minutes here.
Yeah. So yeah, this is my last slide. Look it up. There's a bunch of examples. Here, for example, I take a configuration like this. Hold on. I take a config like this. I want a web server, Nginx, Postgres with the network settings, and it actually compiles it down to a Docker Compose file. So all these examples run. They're runnable in the handout. You can literally just paste them into a Python file and run them. So I hope that this gives you an idea of how this all works. 5 minutes on time. I did it.
Anyone have questions while we have here? And yes, this stuff is freaking wild. I haven't seen anybody who can do the level of wizardry that Manuel can on this stuff, but I'm getting closer as I follow along, and I bet you can too.
It looks like magic, right? But it is like I obviously recommend, and I made in the handout. I made a list of let me call this up. How does this work in handout? So there's a whole handout which is a written up version of the slides, right? So you don't have to read slides. It's LLM generated. I tried to do my best to remove like LLM yap, but at the end, I've got a list of the books that really influenced me and taught me all this stuff. I highly recommend this one. It has AI in the title. It's actually not that much about AI, but Paradigms of Artificial Intelligence Programming by Norvig. Norvig is a stellar programmer. Like he's able to write Python code that looks like a DSL, but it's Python. It's freely available online. It's a Lisp, which, you can use Lisp, but I think people ported this to Python. And it actually has a lot of all these AI problems, the earlier ones, they're just AST walkers, right? And then Eliza, he shows how it's just a pattern matcher on an AST. And then like you'll see it all comes together, but it goes all the way down to a product compiler, natural language unification grammars, like all this stuff that's really interesting in the context of LLMs as well, with parsing natural language as ASTs, all of that stuff. But it's also just a great programming book. It goes into optimization of code, all of that stuff. Absolutely brilliant. Best programming book I've ever written.
Real quick in the chat around when you reach for ASTs, versus DSLs?
So they kind of go hand in hand because an AST is just a data representation of my DSL stuff, right? So every time you have a DSL, you actually have an AST hidden in there. Sometimes it's more explicit than in other cases, but it's always in there. So AST is just a foundation of working with DSLs, is how I would call it. And the boundaries are blurred, right? Like when does a DSL stop being data and become code? It's hard to say. There's a bunch of other things. So crafting interpreters is more about writing programming languages. I'm not sure if this is all that useful. It should be the second one. This one here, structured interpretation of computer programs, is kind of like the wizard version. It like kind of, if you like this like Hofstadter, Strange Loop, Gödel-Escherbach stuff, that's a book for you. It took me a long time to really get it. There's simpler, more pragmatic ways of getting there. For example, paradigms of artificial intelligence programming. So the handout, by the way, I am going to link it in Discord. I linked it yesterday, but yeah, it's probably not going to be there. Let me just quickly grab it. And then the slides are linked here as well. So yeah, this is the handout. So let me push this into AI in action plot. There we go.
Awesome. Well, thank you, Manuel. Thank you, everybody. We will be back again next week with something. If you, I don't know what.
Let me add something to Terraflow. The Dragon book is not great. It's quite antiquated and spends like 80% of its time on parsers. Don't look at it. Like people love touting it. It's in the Hackers the movie, which is really funny. Don't use that one.
All right. Cheers, y'all.
Sorry.
We're at time. Take care.